Most people know that gases expand when heated and contract when cooled. If you've ever left a balloon out in the sun or put it in your fridge for a while, you'll have experienced this firsthand. But why does this happen? Why is there a relationship between temperature and volume? The reason for this is that temperature is a measure of the average kinetic energy of a group of particles, which is the amount of energy contained in their motion. The air molecules inside a balloon at room temperature are zipping around at about 1,000 miles per hour. And when we say that the temperature of that air increases, we're saying that they're moving faster. As they speed up, they push outwards more, causing the balloon to expand. So if temperature is the kinetic energy of particles, what does this mean for solid objects? What's the difference between a hot pan and a cold pan? Well, molecules in solid objects are held together tightly, so they can't actually zip around like in a gas. Instead, when they absorb energy, they vibrate in place. A hot pan is then one whose molecules are vibrating more than a cold one. Now, just like molecules in a hot gas tend to spread out more, the vibrating molecules in a hot pan will also push a bit further from each other. So this means that solid objects also tend to expand when heated and contract when cooled. Because the molecules are held together tightly, the effect is less pronounced than in a gas. Even so, over large distances, this can produce a significant effect. You might have noticed driving over these sorts of finger gaps that are built into bridges. They're called expansion joints, and they allow the bridge to vary in length a little bit without buckling when the temperature changes. The degree to which a material will change size with temperature is called its coefficient of thermal expansion. Most gases expand at about the same rate, since they can be thought of as independently moving particles, or ideal gases. Solids behave in more complicated ways, though. As a general rule, materials with stronger bonds tend to change size less. Stronger bonds correlate with harder materials, so hard materials will usually have lower coefficients of thermal expansion. These coefficients are measured in how many millionths of its own length the size of an object increases with each added degree Celsius. Diamond, which is obviously a very hard material, has a coefficient of 1. Silver has 18, and rubber comes in at 77. So to give you an idea of what these numbers mean, if you had a meter-long rubber eraser in your freezer, and you moved it outside on a hot day, say going from 0 to 30 degrees Celsius, it would get about 2 millimeters longer. You can take advantage of these different rates of expansion to do some interesting things. Take, for example, the classic Mercury glass thermometer. Mercury has a coefficient of 61, while glass is only at 8.5. The idea is that the pool of mercury expands significantly when the temperature rises, but the glass encasing it doesn't. As the mercury expands, it's forced up into a very thin tube. The height it reaches can then be used to precisely measure its relative expansion, giving us a measure of its temperature. Nowadays, we avoid mercury because of its inconvenient toxicity, and the stuff in thermometers is usually ethanol, which has a coefficient of 250 and is traditionally dyed red. Another cool application is what's called a bimetallic strip. This is simply two different strips of metal, usually iron and copper, joined together. Iron has a coefficient of 11.8, while copper comes in at 17. When the strip is heated, the copper will want to expand more than the iron. Since they're joined together, though, the copper isn't able to get longer freely, and the overall effect is that the strip bends. This can then be used to regulate a circuit, for example in an electric tea kettle. If a bimetallic strip is holding the heating circuit together, it can bend and deactivate the circuit when a certain temperature is achieved. As the kettle cools down, the strip will bend back and start the heating process over again. This way the kettle will maintain a reasonable temperature to keep the water boiling without overheating. The same trick is used in most thermostats, except that we need more accuracy so that you can have control over your home's temperature down to the degree. The way to improve the sensitivity of a bimetallic strip is to make it much longer, so that the same curvature will result in a larger displacement of its end. The strips are built in spiral form to save space, resulting in a metal coil that will wind and unwind with changes in temperature. Now all we need to do is attach a wire to one end of the spiral and fix the center in place. The strip will carry the wire around as the temperature changes, activating or deactivating the heating circuit for your home. Now if we add in the ability to rotate this contact point around, we can change what temperature your heater will turn on at. And this is how we end up with the interface you're probably used to on your home thermostat. The same coiled bimetallic strips are also used to regulate fridges, air conditioners, and even those little dial thermometers you might have used at your last barbecue. So that's how we can take advantage of thermal expansion to make useful temperature-sensitive gadgets like thermometers and thermostats. Thanks for watching Explaincast. If you liked it, please rate and subscribe.